I'm Ben Mikek. This is joint work with my advisor, Qirun Zhang at Georgia Tech. So I'll start with a background on SMT constraints. These are first-order logical formulas that are used to encode lots of problems that are relevant to program analysis. Most of you almost certainly use software that's been verified in one way or another using an SMT solver. In this talk, I'm going to split SMT theories into two parts. So first, we have bounded theories, where every variable can have one of finitely many possible values. So this would include bit vectors or floating point numbers. And then there are unbounded theories, where every variable could have any of infinitely many possible values. You can think of integers or real numbers here. So to get into the idea, let's take a look at this example constraint. Here we have integers. These are unbounded mathematical integers, not integers in the sense we usually think of in programming. What's going on in this constraint is that we take the three variables x, y, z, we cube each of them, so x times x times x, we add them up, and then we check whether the sum is equal to the constant 855. So this is a sum of cubes problem. We could ask whether this constraint is satisfiable or unsatisfiable. And with a little bit of reasoning, we could figure out that it's satisfiable. One possible satisfying assignment is x is 7, y is 8, z is 0. But the problem is that, let's take Z3, which is one of the most common SMT solvers. Z3 takes 28 seconds to solve this constraint, which is a very long time, especially if you have to solve thousands of these constraints in a row. So in the rest of this talk, I'm going to ask the question, can we do better? Spoiler alert, the answer is yes. And more importantly, how can we improve on this? So to motivate that, let's take a look at a second very similar constraint, which you see here. We still have multiplication of the variables by each other, except now it's bit vector multiplication instead of regular multiplication. We still have the constant 855. The real difference is that now instead of mathematical integers, we have bit vectors with fixed bit width 12. And Z3 can solve this second constraint in just 1/100th of a second, almost instantly. So the question is then how we get from one to the other. We want to translate from an expensive unbounded constraint to a cheaper bounded one, and we call this theory arbitrage. The real challenge is how did we get that value 12? So as part of this endeavor, we're going to, the reason why this is useful is that when we start with unbounded constraints, the search space is infinite. That's not very formal, but it's a good way of thinking about why unbounded constraints might be difficult to solve. And some of them are even undecidable, which we'll see in a second. On the other hand, for bounded constraints like bit vectors, there's a lot of work on optimizing solving for those. So there's MBA solver from PLDI 3 years ago. There's our work slot, which uses compiler optimizations to do that. So there's a lot of effort that's been put into optimizing bounded theories. And we want to take advantage of that. Overall, these mean that bounded theories are easier to solve on average than unbounded constraints, and we want to take advantage of that. So to do that, we're going to convert integers into bit vectors. We're going to convert real numbers into floating point numbers. And in this talk, I'm going to focus only on integers. For real numbers, you can find the details in the paper. The question we need to answer is how do we pick the width of variables? You saw that number 12 that I showed in the example slides. Where did the 12 come from? That's really the story of how we do this. So as any good program verification researchers, our first thought was, well, let's look at the theory. Can we get a theoretical answer to what that width should be? So there are 4 variants of constraints that we care about, real numbers and integers, and each one of those has a linear and a nonlinear fragment. Linear integer arithmetic constraints do have theoretical bounds, but those bounds grow exponentially in the number of assertions. So that grows way too quickly to be practically useful for most constraints, so we can't use it in that case. Real arithmetic is even worse. It doesn't even have any theoretical bounds at all. And nonlinear integer arithmetic is the worst yet, because not only are there no bounds, it's actually undecidable. So these results are summarized in this table. And what you can see is that for none of the theories do we have practical bounds. And in fact, for only one of them do we even have theoretical bounds. So the answer to can we use the theory? No, unfortunately, the theory won't get us there. The second possibility that might occur is can we pick bit widths that are fixed over all constraints. So let's just pick 16 or 32 and go with that. Can that work? This graph shows the results of doing that. On the x-axis, we have the number of bits. And on the y-axis, we have the solving time. It's normalized to so 16 bits is 1. And as you can see, as the number of bits is increasing, the solving time is going up. This happens because when we expand the bit width, the solver has more to reason about. It's more complex, and therefore it takes longer to solve them. So based on this graph, I would turn to this and say, let's always use 16 or even 8. We always pick a small bit width, and we're good to go. Unfortunately, that doesn't really work, because in this graph, we still have bits on the x-axis. But on the y-axis, we have how many cases does the satisfiability change when we convert from unbounded to bounded constraints with each of these bit widths. And here, we see that as we increase the number of bit widths, the number of cases where we're wrong is going down. This is because if we pick a small width like 16, 16 bits might not be enough to represent all of the satisfying assignments or some of the intermediate computation that's needed in the constraint. So these two graphs, unfortunately, point in opposite directions. Smaller widths are faster to solve, but more likely to be wrong. And larger widths are slower to solve, but more likely to be correct. So there's a bit of two countervailing forces here. And unfortunately, this means that can we naively choose fixed widths? The answer is no. That wouldn't produce good performance because of these conflicting phenomena. So instead, we turn to abstract interpretation to infer bounds per constraint. In abstract interpretation, we have a concrete domain. In our case, that's the semantics of the constraint. And we need an abstract domain that's an approximation of the semantics of the constraint. And so in this paper, we choose an abstract domain corresponding to the largest necessary bit width that's necessary to represent a computation. So to make that a bit more concrete in your minds, here I have the abstraction and concretization functions we use for integers. The abstraction function is taking a set of integers, the absolute value, finding the largest one. We have the log base 2 of 10 because we need to convert from base 10 to binary. And then we add 1 because we still need to represent the possibility of negative numbers in 2's complement since we took an absolute value first. Then the concretization function is doing the opposite. There we take a width and we just return the interval of values that can be represented using that width along with the values true and false because those are always included in SMT constraints. This is the abstract semantics we use for integers. I won't go through every detail of it, but I'll point you to, for example, the addition line, where we take, for addition, the abstract semantics are that we take the maximum width of the two children and then add 1. We add 1 because addition can overflow, but it can only overflow by 1 bit. So the maximum width you would need after addition is 1 more bit than you started with. So we have this written out in formal form and abstract interpretation in the paper, but it's actually quite simple abstract interpretation, so I think a graphic example is useful. Here we have another constraint where we assert that a minus b should be less than 0, and I've converted it into a syntax tree. We're going to follow a very simple abstract semantics here. So the constants are just given their fixed width. So in this case, the constant 0, you only need 1 bit for that. Next, we're going to make an assumption. For variables, we're going to use the width of the widest constant. In this case, that's 15, so 4 bits. Keep this assumption in mind. We're going to come back to this later because this assumption could be wrong, and we're going to have to deal with that at the end. Then for subtraction, it's the same as addition. We can overflow by 1 bit. So we take the maximum of the children, add 1, we end up with 5. And the comparison, we just take the maximum of the children and end up with 5 bits to represent this entire computation. And indeed, 5 bits is enough to represent the satisfying assignment of this constraint, which is A is 15 and B is 16. So going back to our kind of list of possibilities, abstract interpretation can produce bounds for each constraint that produce good performance. But now we have to go back to the thing I told you to remember, which was the assumption we made about variables. Unfortunately, the theoretical result tells us that the width we pick cannot always work. So sometimes we're going to be wrong. And the reason we could be wrong is not because the abstract interpretation is sound, but it's parametric in terms of whatever assumption we made about the variables. And so that assumption could be wrong in some cases, and it's impossible to tell in advance whether it was wrong or not. So instead, we introduce a verification at the end to make sure that the bounds we chose were correct. The way we do this is by following portfolio methodology. So we run our approach and a solver in parallel and use whichever result is produced first. And And if the final constraint is satisfiable, then we can check that the satisfying assignment matches the original. If the final constraint is unsatisfiable, then we just revert to the original and don't produce any performance improvement. So if the result matches, then we've given the user a big speed up. If the result doesn't match, or if the constraint is unsatisfiable, we revert to the original, and we give the user the same performance they would have had originally. But in both cases, we give the user the correct result. So we're maintaining correctness. That's the important part. So overall, we need to introduce this extra verification step, and once we have that, we're almost done. We can move on to the experiments. So we've tested this on the 4 subject logics I've told you about with 2 solvers, Z3 and CVC5. We've implemented the tool as an open source tool called STAUB that you can access through the paper. And we want to ask 3 research questions. So first, does theory arbitrage improve performance? Second, can it unlock performance improvements from the other existing approaches for bounded theories I told you about? And third, can it improve a client analysis? So we seek to answer all 3 of those questions. So for the performance question, this is a table that shows the number of cases that timed out on a vanilla solver and that our approach was then able to solve within the same time limit. You see that for CVC5, we were able to solve more than 3,000 constraints that it timed out on from the benchmark set. And moreover, if you look at the 3 different columns here, we see that abstract interpretation is really the part that's contributing the most here. If we pick fixed 8-bit widths, we only solve 180 extra constraints. If we pick 16 bits, we only solve 60. But if we use abstract interpretation, we solve 300. So the abstract interpretation approach substantially outperforms any fixed width choice. You can see the same phenomenon here. This is a table showing the average speedups. Over the cases that we can verify, there are 8,000 of them in this benchmark set, we provide an average speedup of 1.8, so almost 2 times over those cases. That translates to, over the entire benchmark set with 25,000 constraints, about a 20% performance improvement. And again, the performance improvement is much bigger when we use abstract interpretation than if we use either fixed choice of bit widths. And then for the second research question, whether we can unlock the bounded speedup that's produced by existing approaches, we see that indeed we can. So we go from about a 20% performance improvement to almost a 50% performance improvement that is unlocked by our approach using the existing optimizations for bounded theories. This is a graphical representation of our results. The values along the diagonal are cases where there's no performance improvement. It's the same for the user. The values along the right are cases that you've seen where it was timeout before and now we can solve it. And the cases in this triangle are cases where there's been some performance improvement. And you can see it's fairly randomly distributed through that area. And finally, for the last research question, we used an existing tool called the Ultimate Automizer that competes in the SVComp competition that tries to prove termination of programs. It uses SMT solver calls internally. And for this tool, we pared down the benchmark set to those cases that arrays weren't involved because we don't support arrays. And for those cases, on the verified cases, we got about a 3 times speed up. And then overall, that translates to a 9% performance improvement. And this is important because this case is a very pessimistic use case of our tool, because in termination proving, almost all of the constraints are unsatisfiable, which are the cases we don't improve. So even in some sense, the worst case scenario for our approach, we can still provide some real performance improvement for users. Overall, our approach is to transform expensive unbounded constraints into cheap bounded ones. We call it theory arbitrage. And we achieve this by performing abstract interpretation to infer widths, and then add a bound verification step at the end to maintain correctness. A couple of notes on future work. First, there aren't any bounded theories for strings or arrays, but if someone wants to make one, we could apply this strategy to those. And if we had some extra domain knowledge about a particular set of constraints, then we could use that domain knowledge to inform what widths we pick instead of abstract interpretation, and then we might be able to skip the bound verification step that goes at the end. And finally, we could make further optimizations for real numbers, which I didn't talk about much in this talk, but you can find more about in the paper. So in conclusion, theory arbitrage is transforming unbounded constraints into bounded ones to get a performance improvement. We do bound inference through abstract interpretation. And we do bound verification at the end to make sure the user is always getting the correct result. We've implemented this as an open source tool called STAUB that's available on GitHub and archived on Zenodo. And with that, thank you, and I'd be happy to take any questions.
We have time for a few questions.
Thank you for the excellent talk. And I have a question about the verification part. Does that mean that for any possible assignments to the bound, you can verify whether the result is correct, or just specialize it to the way you calculate the bounds?
No, it would work for any choice of bound.
Oh, so I'm curious that why not just use, for example, abstraction refinement to refine the bounds when the verification part failed? Yeah, because you said that you will totally roll back to the normal solving procedure if that failed. But I mean,
yeah, that's a good idea. So one possible avenue for future work would be a clever way of doing that. You can't do it in a very simple way. We explored that because if you refine the bounds, you then have to solve the constraint again, and solving the constraint is really what takes a huge amount of time.
Oh,
so I mean, if you have, I don't know, 2 or 3 rounds of refinement, maybe like running the new constraint 3 times is still faster than the original. But in general, because you have to stack the solving time every time you do a refinement, the running time of that grows pretty quickly, and it becomes a challenge.
Yeah, that makes sense. Thank you.
Hi, thank you for the talk. Very nice results. I was most curious about the unset case, and in the results where you showed a 9% improvement there. It sounds like you were saying that your approach mainly speeds up the SAT case. So could you comment on where that 9% improvement is coming from?
Oh, the 9% improvement is cases that were satisfiable. So for the unsat cases, we don't improve it at all. It was just that there were a few, I think it's like 8 out of 90 cases are satisfiable in that example.
Okay.
So yeah, it's just a small number of satisfiable cases.
Okay, got it. Thanks.
Benchmark.
Thank you for the interesting talk. So it seems that you have an external tool for your technique. Have you considered implementing your technique into the existing solvers?
Yeah, that's definitely good future work. We wanted to write it as an external tool so that it would be compatible with multiple solvers. And I think I didn't really talk much about it in the talk, but you can see in the tables, the results are slightly different for Z3 and CVC5, but there's still a performance improvement. And like for individual constraints, there can be a big performance difference between different solvers. So we wanted it to be compatible with different ones, but definitely we'd like to implement it within a solver in the future.
Great, thank you.
So I have 2 questions for
Yeah.
you. So when you do abstract interpretation, how much time does it take? Does your speedup actually include the time taken to do abstract interpretation?
Yeah, all the speedup measurements you saw count the time for abstract interpretation and the time to do the verification. That's included. And in the paper, we have a table that shows that time. But basically, abstract interpretation and bound checking are almost negligible compared to the solving time. It's really small.
Cool. The second question is, there are alternative methods for satisfiable formula. Like for example, Zhang Zhu at TTS Zurich has this XSAT solver where they model the problem of checking satisfiability to a combinatorial optimization problem, and that provides some impressive speedups with real numbers, theory of reals. Have you compared your tool with XSAT or its variants?
I haven't, but that would be an interesting thing to do. We might explore that in the future.
Okay. Any more questions? Let's thank the speaker once again.